So we are very happy to have Benoit from the Nova University and Institute for Quantum Optics and Quantum Information in Innsbruck. And he will tell us about probing entanglement and scrambling via randomized measurement. Please start.
Thank you very much. And I would like also to thank you very much for a very kind invitation. Peter Zoller, my former boss, was supposed to talk about today, but unfortunately he could not make it. But he was really essential in what I will discuss today. I had a quick look also at the GeoFlow project, and I'm really amazed by this project and all the great people that are part of this. I knew a few members, and I say hi to everybody, of course. So today I would like to discuss recent projects which were done in Innsbruck when I was still there until 2019, and which I still continue now that I am in Grenoble, again in collaboration with Peter Zoller in Innsbruck, about trying to measure entanglement and related quantities in state-of-the-art experiments. And really our starting point is to take into consideration these experiments which are being developed all around the world. And in all these experiments of synthetic quantum systems, the goal is to create a many-body quantum state based on assembling different elementary constituents. So you can first think of atoms, and atoms at a quantum level can interact with another atom at the quantum level, and then you can realize many-body systems of ultra-cold atoms. Here I show you a picture from Emmanuel Bloch's group, or also from Antoine Brouwer's groups, where the atoms are here in a Rydberg state, so they can strongly interact because they are in a highly excited electronic level. Also a picture of the group of Michel Lukin in Harvard. Another platform of interest is, of course, trapped ions, where the ions also excited in different electronic levels form qubits, and this can be used to create many-body quantum states. And you can also think of now superconducting qubits. So instead of atoms, you have artificial atoms, and these artificial atoms form qubits. And this is also very promising to create many-body quantum states. So in all these platforms, you have unique capabilities to create many-body quantum states. And I want to emphasize that you have also unique opportunities compared to a natural real-life quantum material. You have unique possibilities to probe, to measure these systems with a unique degree of control. And this talk is really about the measuring aspect. So we consider that one can create a very nice quantum state, which is relevant for various applications. And my goal will be to explain how we can measure interesting physical quantities associated with these many-body states. And so what kind of application I have in mind? I have in mind, of course, two types of application. The first is quantum simulation. You want to create in the lab a many-body quantum state associated with Hamiltonian, which is relevant for, let's say, condensed matter or high-energy physics. And I think for GeoFlow, it's more high-energy physics, gravity part, which is of interest. And by creating this state in the lab, you want after this to measure some interesting properties associated with this state. And it's really, in the end, the measurement will give you some information about the physics you want to study, right? Second type of application is quantum computing, where you want to run a quantum algorithm. And the quantum computer can also be used to study quantum simulation, because it's also a many-body quantum system. Also, in this case, in the end, you would like to perform a measurement, and in the end, you would like to perform a measurement which tells you something about the quantum nature of your many-body quantum state. So in both of these applications, the measurement plays a central part. So now, how a measurement is typically done in this experiment with many-body quantum states. So it's actually simple. You always create a simple initial state, a state that you can create with very high fidelity, which is your starting point. So in my example, I show you a qubit system with 4 spins, 4 qubits. This I can create efficiently. Then the second step is also kind of easy to imagine, to consider, that I evolve the system and I create now a many-body quantum state, which will be relevant for quantum simulation or for quantum computation. This is my state of interest. And I denote this state by a density matrix rho. And then the final step of this timeline is to take a projective measurement. So the same kind of measurement that you see in quantum mechanics 1 lectures, you take a projective measurement. And if you have spins in mind, you will measure a spin configuration. So here in my example, I see spin up, spin down, spin on, spin up. And by repeating this a certain number of times, I will be able to build statistics and to have access to the probability. So it's an expectation value, the probability to see a specific spin configuration S, plus a little bit of short noise, which can be reduced. So by doing this, I will measure a property of a density matrix, but the problem is that I can only have access to expectation value of observable by definition of quantum mechanics, so to say. And I will not have access to nonlinear quantities of a density matrix if I just do that. Okay. But let's first consider observable. And in quantum simulation, the measurement of observable is actually essential. So if you have a many-body quantum states, the observable are typically densities or also correlation functions. So let me take the example of a cold atom system. So what you have in this experiment is you have the atoms hopping in a lattice, and at the end of the sequence I showed before, you take a projective measurement. So you take really a picture of the atoms. This is what it is, by measuring the photons from a fluorescence of the photons of the atoms. And then from this image, you can reconstruct the expectation value of different observables, such as correlation functions. So here, just look at the image, okay, and you see that the atoms would like to be in an antiferromagnetic order. Okay, this is very apparent. And because it's apparent, it's easy to quantify these expectation values by accumulating a lot of images. Here I show you a picture from a paper by Emmanuel Bloch's group. We can reconstruct the correlation function of this system. And you can go also higher order, consider 3-point correlation function, string order. So this is very much a successful story in quantum simulation, the ability to measure correlation function at the single site level. I wanted to emphasize this point before I go on. But as I said, by doing this, you can only measure, by definition of quantum mechanics, expectation values of observable. Now in this work, we have been developing new ideas, also based on works by other groups, to go beyond measuring expectation values of observable. That's kind of what we do at the moment. And our recipe is actually simple, at least from a conceptual point of view. And what we have in mind is to take the standard scenario of measurement in a quantum device and add a single additional ingredient. So first, we have in mind an initial state, which can be prepared with high fidelity, then evolution, just as before, and at the end, there will be a measurement. Okay? But what we want is, before the measurement, we want to add a random operation. Okay. This means that when we will take a measurement, the probability to observe a certain state will be no longer a single number, but it will be a random number, which is sampled according to the distribution of unitaries I'm using here. Okay. And our claim is that the statistics of this random numbers, because you have different S, is extremely rich. And it's actually amazing how we can think about this random number. I will give you a bunch of examples later on. So when you look at the statistics of this, so you take, for example, cross correlation between two measurements. You measure S1, given spin configuration, and measure S2. You take an n-sample average over random unitaries. You will get effectively a quantity which can be the entanglement entropies. We have also shown that you can measure fidelities. In this talk, I will show how to measure properties of scrambling based on these ideas. You can also measure topology.
Benoit?
Yeah.
May I ask a naive theorist question? If you really averaged over, if you really tried to deal with random unitaries, I would have expected that those are very complex and difficult to implement in an actual experiment. Is that really what you have access to?
That's a very good point. You're asking about how to implement a random unitary in an experiment?
Yeah.
Yeah. So I will show you two big families of randomized measurement. One is based on random unitaries, which are difficult to implement in an experiment. These are completely chaotic unitaries. And in this case, the random matrix theory that we use to prove our protocols is very easy. And the second big family of randomized measurement is based on using simpler random unitaries from an experimental point of view. So these are tensor product of local random unitaries. In this case, it's more complicated to do the random matrix theory to establish a protocol. When this protocol is proven, then the experimentalists can just use it and it's easy for them. So two families of protocols, one with global chaotic random unitaries, one with local random unitaries.
That's very striking to me that you have that capability. How large are these systems? What's the size of the Hilbert space here?
And so in the experimental works, we were able to achieve this measurement for up to 12 qubits. So it's kind of, it's already a many-body quantum system, but it's not, it's maybe not what you want to describe a black hole, but it's in this range.
I find it surprising. I mean, that's amazing. Yeah, thank you.
All right. I don't hesitate if you have other questions. So before I dig into the details of how to apply these techniques for measuring scrambling, I just wanted to highlight a few results where these techniques were first applied. It gives me also the opportunity to thank the collaborators from the experimental groups. So first, the first time these techniques were proven and demonstrated was in the context of measuring the second Rényi entropy. So it's a quantity which is non-linear with respect to the density matrix. So it's a good test case for randomized measurement. And it's also a quantity which can be used to detect and quantify entanglement, mixed state entanglement. And this was done in Innsbruck with 10 ions. And I don't explain the protocol, but I just show you that we could measure the entropy for different partition size. So I is a partition size up to 10 qubits. And the different colors mean different times. So you see that first the entropy is small, low level of entanglement, and then it kind of increase as a function of time. If you look at subsystem, while the full system remains at a low level of entropy. So it means the kind of full system is well isolated. And recently we could also collaborate with Google people and repeat these experiments in 2D. And in 2D is very interesting because you can study the space-time profile of entanglement. And what we could observe, so this is preliminary, but we can observe that in this case, what I show is the entropy as a function of time. And now the different lines are the different size of the partition. And you can see that you have actually a transition for different type of scalings. At initial time, all the entropies are kind of small. You expect a area law of entanglement. When at late times, you reach a volume law profile, which is expected if you have a formalization. You can also measure quantities associated with a partial transpose of a density matrix. So it's called the positive partial transpose condition. And this is a work we could do with a group of Pasquale Calabrese, Marcello Dal Monte in Trieste, and John Presqu'île in Caltech. And in this case, you measure this quantity Pn, trace of rho partial transpose to power n, and then you can also quantify entanglement in a more refined way compared to the entropies, and study also how entanglement spreads in a many body system. Okay. So these are really the latest results. And today I will talk about something which was done 2 years ago, actually. So it was the second randomized measurement protocol, how to measure quantities related to scrambling. So this is more a topic of this talk. And this was a theory work first with myself. Andreas Elben was in Innsbruck, and he will join Caltech soon. Lucas in Innsbruck, Norm, was very useful to help us understand this result, and Peter from Innsbruck. And then I will present quickly the experiment also done in Innsbruck, how to measure these quantities in the lab. So now I will really present the details of the protocol. So first, what we would like to measure is the following. We have time evolution going on, and this is described by a time evolution operator U. And we are in the Heisenberg picture. So what this means, I consider initially an operator W, which is in this qubit example, a Pauli matrix. And I'm asking the question, how this operator evolves as a function of time. So if I have, let's say, a quantum gate model, initially the W is my initial W, of course. Then if I apply one layer of local gates, and W will be made decomposed of 2 qubit Pauli matrices, which is this orange box, and so on. So the size of the operator will grow as a function of time, and I'm asking the question, how does it grow? And to quantify this, one can introduce a quantity which is called out of time ordered correlation function, so OTAC or OTOC. And the meaning of this quantity is that I compare W of t, so the operator which evolves, I compare it with V, an operator which does not evolve. Okay, so this acts as a reference, if you want. And you can see that initially I will consider an operator V which commutes with W. So initially the commutator of W and T and V is 0. And you can see that the order has to be 1 because I can just swap these two terms. And then as time goes on, W of t will spread in the qubit space. And eventually, in this space-time picture, you see that the extreme position of W will reach V. At this point, the two operators will no longer commute. And the OTAC will be able to detect this fact, and it will be smaller than 1. So the decay of the OTAC represents somehow the fact that the operator has spread until the position of V. So this is my picture of OTAC in the qubit system. But it's actually very rich, and it has been studied in many models, including in quantum gravity. I'm sure many of you know about this much more than I do. So in the context of model like the SYK model, the decay of the OTAC is actually exponential, and the exponent associated with this exponential decay is maximal in the sense of it saturates a predicted bound for chaos. in models which are maybe more realistic now for the present experiments with synthetic quantum systems, the decay of the OTACs is also universal. So in many models, you have what is called a butterfly velocity. I mean, the decay of the OTACs always occurs at a time which is proportional to the distance between the initial W and the V. This is an example here in the middle panel. And you have also models where the decay of the OTACs is universal in the sense that it's slow, governed by not governed by, relevant for a phase called many-body localization. In other words, by measuring the OTACs, you can classify the different types of quantum dynamics that you have in the lab in many-body quantum systems. So that's what makes it very interesting for me. Now the problem is a little bit how to measure this beast. So I recall the definition of the OTACs here. And you see that you have twice the time appearing there. So it's not a standard expectation value of an observable. In particular, if you write this state rho as a pure state, you can rewrite the OTAC as an overlap. Actually, it's an overlap between two states, psi1 and psi2. And I can write psi1 as the evolution of a quantum system with U, application of W, which I assume unitary here, and then reverse evolution U dagger, and then V. And psi2 is more or less the same thing, but in a different order. And therefore, to measure the OTACs, if I do it very naively, and as in this case, I will need to first be able to implement the evolution and the backwards time evolution, which is something which can be difficult. And I will also be able to need to be able to measure an overlap, which is non-trivial. And there are actually many proposals which implement many tricks to simplify this procedure, of course. But in all these protocols, you need to either be able to reverse time evolution, so be able to implement U dagger, or use tricks to avoid this using interference effect like copies and auxiliary systems. And on the experimental side, there were now three main experiments measuring OTACs based on this family of protocols, so with NMR systems and trapped ions. And this was actually remarkable because you need this extreme level of control in your hardware. And there was in particular an experiment by the group of Chris Monroe implementing an idea from Benny Yoshida and Norm Yao, where the OTAC could be measured in a qubit system, and the effect of decoherence was also taken into account and then filtered out to really measure the true unitary part of the decay of the OTAC. So this was a remarkable experiment I also wanted to highlight. For randomized measurement, the goal is to allow access for measuring OTACs in new systems. Okay, so system where you cannot, you are not able to reverse time evolution, and you don't have auxiliary systems. Are you still able to measure OTACs, and does it also make your life easier if you have a standard quantum system? And so this is why we propose a protocol in this context, and the goal that it's also applicable for large-scale quantum system. So how does this work? And this is also related to your question, Raphael, about what kind of unitaries we need. So to measure the OTACs based on randomized measurement protocols, I need to do a little bit of explanation, of course. The protocol is you can think of an experimental recipe where I will do two measurements. In these two measurements, I always start by creating a random state. And this state is just a product state multiplied by a random unitary U. And here I consider U from the circular unitary ensemble. So it's in principle an entangling operation. Then I will time evolve with the unitary operator of interest U.
Benoit, can I interrupt briefly?
Of course, yeah.
Yeah, so I think that it would be helpful to give a little bit more statements on how you're actually implementing the random unitary. And
Yeah,
one,
I come to that. Yeah.
well, like let me just explain why briefly. So one reason why that's the case is because a lot of the more high energy minded people in the collaboration are used to thinking of random unitaries like hard random unitaries, so like exponentially complex.
Yes.
Given that you're implementing a random unitary on a small Hilbert space, I think that people would appreciate, I guess, a more direct clarification of what exactly you mean when you say a random unitary in this case.
Yeah. So at this point, I consider that,
and also why it's easy to implement for you guys.
Yeah. Okay. Yeah. So to explain this first protocol, I just consider that U is taken from the R measure, which is something which is hard to implement in a many-body quantum system. And then in the second step, I will consider another distribution of random unitaries, which will be the one which will be then implemented in the experiment. Okay, so this will be in my next slide. Okay. So first, I consider for simplicity that it's taken from the R measure, and then I will take a simpler distribution, and then I will connect to experimental work. All right. Okay. So suppose just for a moment, I'm not explaining how to do this in an experiment. I'm able to apply in an experiment a unitary from the R measure. So it's a completely random matrix. Then I apply a time evolution operator, capital U, and then I will take a measurement W. So this is a complete time ordered sequence, of course, and I'm able to take this expectation value, to measure this expectation value, I get W. In a second experiment, I will do exactly the same thing, except that I will apply an operator V after the random unitary and before the time evolution operator of interest. And I will get a second expectation value, VW of TV, which has this expression. Now, our claim is that when you look at the statistical correlation between these two measurements, this statistical correlation is equal to the OTAC. It's actually the same thing. And this denominator is very similar to this. It's just that I don't have a V here. So it's just a scaling factor. And this equality holds because I'm taking the R measure. This is the essential assumption here. And now you can try to get some insight why this equality holds. And for this, you can just consider limiting cases. If you have U equal the identity matrix, so you have no evolution, then you understand that the OTAC is 1 first, it's obvious, but you also understand why the right-hand side is also 1. It's because you are comparing a measurement of W here on the left-hand side with another measurement of W here on the right-hand side, which is only perturbed at a distant location. So whatever you do here cannot influence what you measure there. So the two measurements has to be perfectly correlated. This is the meaning of having the OTAC equal to 1. Now at late times, U is able to scramble your system. And then when you act with V, you are able to change the measurement of W, which occurs there. Therefore, the correlations are affected, and the OTAC will be typically smaller than 1. So I will skip the proof because I want to spend more time on connecting to experiment and introduce simpler protocols. So I can maybe come back later to the proof based on the techniques of R integration. But now I want to, because I already got 2 questions about how to implement these unitaries in the lab. I will now come to this point where I presented a first protocol where I'm able to measure OTACs based on U sampled from R measure. The point is, in an experiment, these unitaries are hard to implement because this is a chaotic unitary. So what we proposed is to replace these global unitaries, this entangling operation, by local unitaries. And this is now the unitaries I will be using. And these unitaries were also used in the experiment. So this is the take-home message is that you don't want to use hard random unitaries, you want to use local ones. Okay. And now, please ask me again the question if you're confused. The unitaries I want to use now are considered a qubit system, and these unitaries are completely local. Okay, so if I have 5 qubits here, I will apply a local qubit rotation on qubit 1, local qubit rotation on qubit 2, and so on. So this is the distribution I'm considering. And this can be implemented with very high fidelity in the lab. Okay. So this is a new distribution of random unitaries, but the protocol is the same. The math, yes.
Yeah, actually, I feel like I should ask the question again because now I'm confused in the other direction. So originally when you were talking about Har random, if you could implement it, I would totally believe that like you can get these theoretical results that you get with OTAC. But now when you're talking about like essentially a tensor product of 1 qubit random rotation things, is there an intuitive understanding of why this is sufficiently random? Because it's a very special substructure, a tensor product specialized substructure in the space of Har random matrices, right? This isn't even like a 2 design thing.
No, it's not a 2 design. Yeah, you're right.
And so I guess the surprising thing is that it still works.
To be honest, this was really a surprise, but it still works. And it's not easy to convince you based on a simple argument that it will work. But if you do the math, I guess you will be convinced. And the other thing I can say is that if you take the 2 limiting cases I told you before, these 2 limiting cases are also work in this case with a tensor product of local random unitaries. Okay, so if I have U equal the identity, I can still believe that these 2 experiments will be perfectly correlated. And if U is a scrambling operator, these 2 measurements will no longer be correlated. So I still capture this effect of related to the OTAC. But then it's non-trivial to prove analytically that the statistical correlation are exactly mapped to the OTACs.
So let me just see if I understand you correctly now.
Yeah.
The claim is not that you are able to implement Har random unitaries. The claim is that there are results that can only be proven for Har random unitaries that you are surprisingly able to implement with much simpler unitaries.
Yes, that's exactly, yeah. Now, I want to add something, is that there is a price to pay in terms of statistical errors. The mapping between OTACs and statistical correlation is much more involved when you use this tensor product structure. So the way you treat the data, you accumulate the data is more involved with local unitaries.
It would be really important to understand what's going on there.
Yeah.
Sorry, just to clarify, you said at one point that if you do the math, you can convince yourself. So for the non-Har random unitaries, is it just that you run it and it happens to work in your fix or experiment, or is there a firm theoretical foundation for that?
Yes, you can prove analytically the mapping. The mapping holds actually for this particular structure, but it's an expression which is more complicated, and you can see this expression on my slide. I have the statistical correlation on the right-hand side, and I have to perform a summation on various initial states. I didn't have this summation in the slide before. Okay, so this is the additional complexity when I use this tensor product structure.
Mm-hmm.
So that's what I meant.
Oh,
And,
okay. Not like it's not understood. You just don't have an intuitive explanation.
I know I cannot. Yeah, that's what I wanted to say. So I have analytical result, but it's hard for me to explain just by looking at this result why it works.
Can I ask one question?
Yeah, of course. Yeah.
Are you saying something set of 2 to the n initial states?
Yeah.
Can all these 2 to the n can be in the basis of product states or have to be entangled?
No, we are on the basis of product state. Yeah. That's
sorry, basis of product states.
Yeah, basis of
okay,
product state.
it's enough. Okay,
Yeah.
thank you.
Yeah. So in principle, I have to use 2 to the n initial states. And in this case, I will measure a quantity which is called ON. And this ON is written in this yellow box. And when n converges to capital N, the system size, I get the OTAC. So it's a matter of sampling initial state in order to converge to a true value of the OTAC. So it's a non-trivial sampling task. But what we found by looking at physical example is usually very small n allows you already to get a very good approximation of the OTACs. So that's the result. And I have not so much time to show you various examples, but I will show you this with experimental data where we used small n equal 2 and we compare with a true OTAC. And yeah, so thank you for very interesting questions. It's actually the whole point of randomized measurement is our challenge is always to end up with a protocol with local unitaries, because these are the ones, but the unitaries are okay to implement in the lab, of course. So your questions are really to a point and perfect. So how much time do I have? Because I'm kind of running late.
10 minutes, 5 minutes for questions.
10 minutes, okay, very good. So I have time for experimental review.
I mean the 5 minutes plus 5 minutes.
5 minutes plus 5 minutes.
But we can take time.
Okay.
Yeah, you got a lot of questions, so we can be a little flexible, I think.
Okay, thanks. So before I move to experimental details and of the second work, there are 2 things I want to mention. First, the role of statistical errors. So to estimate the statistical correlations, you have to repeat the experiment a certain number of times to overcome shot noise. And here the limitations are due to the complexity of the operator W of t. W of t, first, it's a single qubit rotation operator, so it's very simple to measure. It takes its values between -1 and 1. When as time goes on, this operator scrambles over many sites, and typically the statistical fluctuation of this W operator will be smaller and smaller. It will be of the order of 1/2 to the n. As a consequence, the number of measurements you need is of the order of 2 to the n. So this protocol will work for, let's say, 10 to 20 qubits, fully chaotic. It will work for more qubits if it is not so much chaotic, but there will be always a limitation in terms of system size. It's important to mention it. On the other hand, it's very robust against decoherence. And it's because we are taking ensemble averages, and somehow the effect of noise typically drops out when we take these averages. So here I show an example with depolarization where we can show analytically, but the effect of the noise vanishes exactly in this case. You can also measure thermal OTACs. So far I was considering infinite temperature OTAC, where the density matrix is the identity. So it's a little bit more complex, but basically instead of measuring 2-point correlation functions, 2-point statistical correlations, you measure 3-point statistical correlation. You correlate with the expectation value of the energy, and you get the thermal OTAC. But now let me switch immediately to the experiment, where I won't spend much time, because what was done in the experiment correspond to a theory protocol. So what they had is a chain of 10 qubits in a trap time. They could perform this local random rotation, which we discussed. Then they could perform a many-body time evolution with a long-range XY model, which is this one. And then they can take these measurements and measure the W operator. And here I show you kind of the raw data we saw when they did this experiment, and for different times. So I show this correlation. At time t equals 0, you see that the expectation value of W can be anything because I'm always changing the initial state with these random rotations. But what I see is that the two experiments, which differ by the V operator, are perfectly correlated. This means, so here the operators are separated by this distance, but I have no scrambling. The application of V doesn't change what I see when I measure W. So this is perfectly consistent. Now, at time t equal 2 milliseconds, I have what I call naively a bit of scrambling. So it means it's still kind of correlated, but sometimes it is not. Okay, so I can distort this shape, this perfect correlation. And then at time t equal 5 milliseconds, what I see now is that it's completely scrambled. When I act with V on the system, I completely change the result of my measurement, W. And now our mapping, a complicated mapping, allows to quantify this by extracting the OTAC. Okay. So this is shown on the left-hand side, the dots of the experimental reconstruction of the OTACs O2. So it's remember small n equal 2, which is in pretty good agreement with the theory line, which is in the same plot. And on the right-hand side, what I show is the actual OTAC from a theory, not O2, the real OTAC, the real one which I defined at the beginning of my talk. And you have a quantitative agreement. It means the sampling efficiency was correct. I got convergence. Okay. And sorry, I forgot to mention that the different lines represent different position of the W operator here. So you can try now to see if you have a given space-time profile when you measure this OTAC. So what we did, we try to rescale the x-axis as a function of some butterfly velocity v2. So this v2 is extracted from a fit. And when we do this fit, we see that for some range, so this alpha governs the range of a power interaction, we are able to kind of make all these curves collapse into a single wavefront. So this made us confident that we have a kind of a ballistic spreading of the operator. On the other hand, if alpha equal 0.85, so this is more long-range interaction, we are not able to make this collapse happen. And in this case, the scrambling dynamics is more complicated, more richer than a standard ballistic propagation. So we are really able to extract the features of scrambling in this system, and it would be fun in the future to extend this to, let's say, flow K dynamics, or even something more relevant to black hole physics. At the moment, it's just a standard spin model. So what is the exact role of decoherence in this model? And we did not observe any effect of decoherence by looking at the OTAC dynamics. So the experiment and the unitary prediction were consistent, but we observed that there was actually an effect of decoherence when measuring Rényi entropies. And for this, we use the protocol I mentioned before. And we see that as a function of time, if you look at, let's say, 5 milliseconds, the red circles are above, so the experimental points are above the unitary simulation. So there is really a quantitative effect of decoherence on the measurement of the entropies, which we did not observe on the OTAC measurements. So for us, it was a strong evidence that the protocol is actually robust against decoherence. And we observe a second effect of decoherence based on measuring something which is complementary to the OTACs. It's called the operator growth. And it follows from a proposal from also, I think, members of the GeoFlow. Well, instead of looking at statistical correlation between two measurements, you are looking at the statistical fluctuation of a single observer. So you're looking here at the x-axis and you're wondering, how does it fluctuate? So here at time t equals 0, it fluctuates between -1 and 1. When it fluctuates between, let's say, -0.8 and 0.8. So this fluctuation decreases a function of time, and this is believed to be another signature of scrambling, which we could measure. And then we see that we really observe this decay of this fluctuation, but we see an effect of decoherence. So we think it's interesting to always compare entropies, OTACs, and this third quantity to really make the difference between unitary and decoherence in the system. And the randomized measurement protocol allow you to do that. That's what is nice, really based on the same data. Okay, so I don't have time to mention a more recent project for measuring the spectral form factor. I'm happy to answer questions about it later. But obviously, want to thank you for your attention. This is an exciting time for our project, and I'm working basically full time on these new ideas. We want to do many new things. Measuring the spectral form factor was one example. We also found some tricks to reduce the number of measurements to be performed using important sampling. We are trying to measure new quantities also, like tripartite mutual information. So this is what we are doing now, and we are always happy to discuss and collaborate, of course, with all of you. And I also would like to thank you for your very interesting questions, to a point, and very interesting for me. Thank you very much.
Thank you very much. So we have 5 minutes for questions, further questions.
Yeah, and then before you all run away, I'm going to ask that at the end of the questions, Hugo and Masamichi can maybe just give us a summary of the rest of the day and how the various things like Gather Town and the discussions and so on are going to work before we take a break. But yeah, let's go for questions now.
So I have a question. Hi, Benoit. Can you hear me?
Speak up a little more, Xiaolang, if you can.
Maybe a problem with the earphones. Can you hear me better? Yeah. Yeah. So I'm curious about the previous slide you mentioned that experiment about our proposal.
Yeah.
Yeah. So what is the y-axis here? Because in our case, we were just looking at this second moment. The one on your plot on the right side. Is that the one that's?
I guess so. So it's a variance of the W operator over random unitaries.
Mm-hmm. So the figures on the left are for different experiment. I just want to understand on the left as a V.
The figures on the left are the ones I need to extract the OTACs. But for your proposal, I just need the data which sit on the x-axis, the value of a single W. Yeah.
And this is for a random product initial state?
A random product initial state, as in your. So it's the same data as in the OTAC proposal. I just extract this second moment.
And then you're saying this difference. So the blue line is different from the simulation, then that shows that there is decoherence.
So the blue point is experiment, the red line is unitary simulation without decoherence. And the black line is simulation with decoherence. So we know very well the decoherence in this system. And then we get a match when we include decoherence.
What kind of decoherence is there? Is it like a single qubit kind of error, or?
In this case, the dominant source of decoherence is global dephasing, because you have a global magnetic field affecting the energy levels.
I see.
It's not negligible. Yeah.
Okay, thanks. Very interesting. Very much.
Could I follow up on some of these questions about the decoherence? So yeah, I guess I was a little bit surprised that you mentioned the robustness to decoherence, because normally we're sort of afraid that if what you're trying to probe is scrambling and chaos, it should be very sensitive to any kind of imperfection. So I guess I was wondering first whether you could give a little bit more intuition about sort of why you have that robustness, and also maybe why this one is more sensitive. And then maybe also say a little bit like, is the robustness a good thing or a bad thing? For me as an experimentalist, it sounds like, oh, that's nice, but like theoretically, like maybe it says you're not as sensitive to some effect that you might want to be able to, right? So.
No, you're totally right. It's not obvious, but it's a good thing that the protocol is robust. And this is exactly the reason why we wanted to measure other things like entropies and this quantity. So for the OTACs, the robustness against decoherence can be proven analytically for only global depolarization, which is kind of a very specific model for decoherence, which is not always accurate to model experiments, and readout errors. And in this case, you can show analytically the following. The measurement, the expectation of W of t, if you have global depolarization, will be replaced by alpha times the real expectation value of W of t if you have global depolarization. So your expression On of t will be rescaled by a term alpha from the first W, which appears here, times alpha, the same alpha from the second expectation value. The point is that we have a denominator dn of L, which has exactly the same form with two expectation value W and W. So the estimation of the OTACs is normalized if you want. We are looking at normalized statistical correlations of normalized statistical correlation. Therefore, we don't see an effect of decoherence. I can give you a little bit more insight if you want. If this kind of plots can help you. If you have no decoherence, let's say at time t equals 0, you observe that the signal takes values between -1 and 1. If you have depolarization or readout errors, it will simply take values between a restricted range, but still the correlation will be still perfect, right? It will be always the same value. So that's why it's robust. I hope I was clear.
Yes, thanks.
I have a quick question. So, you know, if you look at the full OTAC, there's a lot of structure in there, both in terms, not just in terms of this operator spreading speed, the butterfly speed, but also in terms of the broadening of the operator front, you know, the structure of the operator within the light cone. Are you able to probe those kinds of questions?
So we are able to probe the fact that the operator has a finite wavefront. This we saw in this plots. Now the fact that the operator wavefront broadens as a function of time, we were not able to really see or quantify with respect to numerical simulation. It's very hard to extract, but in principle it's possible. It's just a small signal in this experiment. So what we would like to see exactly, like the fact that it broadens diffusively.
Right.
Yeah. we tried to do it, but we did not succeed.
Okay, thanks.
Any more questions? If not, let us thank Benoit again.
Thank you.
Thank you.